So another thing we're going to talk about today is clustering. Now, clustering is a type of unsupervised learning. Jareen has already taken you through what supervised learning is, and we covered ensembles, which are part of supervised learning. In simple terms, in supervised learning, you have a label and you're trying to predict that. Whereas in unsupervised learning, you typically don't have a label. So clustering is a type of unsupervised learning. In the presentation, I asked a question. Have you ever spent time watching a large crowd? And if so, have you ever seen any recurring personalities? You could go to a market. Of course, after this whole COVID thing, you can go and see if you can try and learn how to read people. But then most times you'll see someone in like a suit, and then you make a conclusion that, you know, guys who are in suits and briefcases are business executives. And then you'll see someone in skinny jeans and shirts and a t-shirt, and then you say, oh, this guy is a hipster or a millennial or whatever we're calling them now. Then you'll probably see a lady unloading kids from a van, and you'll think, okay, this is a soccer mom. Clustering is not very different from this. It's really just getting data points and trying to group them. Like, okay, these guys are soccer moms, these guys are hipsters, and these guys are executives. And so these are the decisions that we need to do with the different clusters that we find out. You will learn that in real case scenarios, we have marketing. This is very good in marketing because it can help you determine what kind of marketing you can do for each of the different clusters that you found out. So for example, the business executives, you typically want to approach them in a different way and attract them in a different way. And then the millennials, you're like, okay, let's put in some digital things in here that might attract them. And then the soccer moms maybe are more interested in something. So you find that this is a typical thing that guys in marketing use a lot to determine how they're going to run their campaigns. So the act of clustering or spotting patterns is not so different from spotting patterns in groups of people. So what we hope you learn after this is, one, the ways clustering differ from classification tests. We've already covered that. And then how clustering defines a group and how such groups are identified by K-means. K-means is a type of clustering algorithm. It's like the most common type that we have out there. Of course, there have been improvements done to the K-means algorithm. And then we'll go through the steps that we need to go through in order to apply clustering in a live example or a real life data set. So what is clustering? It is finding groups of objects such that the objects in a group will be similar or related to one another and different from objects in other groups. So if you look at the example, what we're looking at right now, in clustering, you generally want to minimize the intra-cluster distances. So basically, you want the different data points within one cluster to be very, very minimized, so to be as close to each other as possible. And then you want the inter-cluster distances to be maximized. So you want the different clusters to be as far away from each other as possible, or as different from each other as possible. That's basically what we're doing with clustering. Clustering, still, what is clustering analysis? It's unsupervised learning. We've gone through this. We've said that there's no predefined classes. We have no label. We don't know what we're doing. We don't know who we're looking at. We're really just trying to understand our data, and we're trying to, it's used for knowledge discovery rather than prediction. We're trying to learn, like, what can we learn from our data set? We don't know their labels. What else can we learn? The typical applications of clustering are customer segmentation, like I have mentioned earlier on, that most times marketing will use, where people with different demographics or different buying patterns or whatever are clustered together, just so we understand similarities of those different clusters. It's used to do classification without training. So this is interesting. So if you have a data set and you don't have a label, you can come up with labels using your cluster. So imagine you have a data set and you perform a clustering analysis on them, and you find out that this data set typically has, say, 4 clusters are created from the data set. And then you learn more about these clusters. So you learn that cluster 1, the guys in cluster 1 typically behave like this, and you give them a label of your own. then cluster 2 typically behaves like this, and you give it a label of your own. What you can do is now use those labels that you've created from your clustering to actually now build an actual model using supervised learning. It's a long process, but it's also very good, and it can be done. It can be used to create to detect outliers in your data set. So imagine you have clusters, and then you have a few outliers that appear in your clusters. You might want to look at those outliers with more, to look deeper into those outliers, to just kind of understand why they're outliers. This can be good if you're looking for anomalies, like anomaly detection in a bank or card transactions. You want to see which transactions are likely to be fraud. You might find that majority of the fraud transactions are typically anomalous transactions, and so they will appear as outliers if you perform your clustering analysis. So it's also good for that as well. So requirements of clustering in data mining: your scalability is important. The larger your data set, the longer your clustering will take. Clustering has the ability to deal with different types of data. You can look at nominal data, ordinal data, and numeric data. Then you can discover interesting shapes in your data when you perform your clustering. Minimal requirement for you to perform clustering, which is like the disadvantage of clustering, is you need domain knowledge. So after the model has told you that, you know what, you have 3 clusters in your data set, someone actually has to sit down and understand each of those clusters, to label them, if I might say, to know that for cluster 1, 5 customers have been grouped into cluster 1, and this is how they typically behave. So maybe this cluster 1 are executive customers, or this particular cluster are soccer moms, just based on understanding of the features. So you need a lot of domain knowledge with this. It has the ability to deal with noise and outliers. It is insensitive to the order of your input of records. You typically deal with high dimensionality, and then you need to be able to interpret and use the results. So types of clusterings: we have different types of clusterings. There's a hierarchical clustering and a partitional clustering. Partitional clustering is really a division of data points into non-overlapping subsets or clusters, such that each data point is exactly in one cluster. So you can't have different data points overlapping and appearing in multiple clusters. Each data point appears in one cluster. And then you have hierarchical clustering. So this is an example of partitional clustering. On the onset, if you look at the original points, which are on our left, one can easily see that they have either 3 clusters can be created, or even 2. But remember, we can't have any overlapping data points happening in more than one cluster. So a very good example of a very good cluster is what we see on the right, which is what partitional clustering is, where each data point is put in one cluster, and we end up with 3 clusters, and there's no overlapping that happens. Then with hierarchical clustering, it works differently. Here in this case, you don't really need to know how many clusters need to have existed in your data set, which is also another downside to clustering. You need to have an idea. When you're building your model, it asks you for the number of clusters you want it to build. So unfortunately, most times you find there's a lot of trial and error if you don't know, or if you don't have any preconceived information of how many clusters should be in your data set. So you find that you have to build so many models with different numbers of clusters to see which one makes sense for you. For this particular type of clustering, there's no need for us to know the number of clusters that we want to create. In fact, many times you can use this to help you know how many clusters you should have. So for example, if we look at the first tree on the right, can easily tell you that maybe it's very good for you to have 3 clusters. For this case, it groups P2 and P3 together, and then it will group into one kind of cluster. And then it can say, okay, then we can add P4 as well, and then P1 into one huge cluster. So this is different, but it also gives you information. You can learn a lot about your data when you build a hierarchical clustering. And then, like I said, it can give you information on how many clusters you should build. So for this particular data set, you can either come up with 2 clusters, like these 2, or you can say, I'm going to build 3 clusters, like this, when using your partitional clustering. So yeah, we've gone through this. Examples of partitional clustering are k-means, which is typically, numeric data. We have k-medoids, then there's clarans, and then the EM. And then these are examples of the hierarchical approach. I would recommend that you guys read more about this, but the simplest or the most common is k-means. Another thing that is important in clustering is distance measures, because remember, we look at the distance, the distance within a particular cluster, and the individual data points within a cluster should be minimized, and then the distance between the 2 different clusters should be maximized. So distance is actually a very important thing when it comes to clustering. So I thought it would be very good for us to talk about that and give a few examples of how distance can be calculated in its simplicity. So similarity and distance are important. They are 2 opposite concepts. Similarity measures how close or similar 2 examples are, whereas distance measures how far or different 2 examples are. The definitions of distance and of distance functions are dependent on variable types. So when you have a numeric data type, there's a particular distance function that you can use. And then when you have a nominal data type, there's a particular distance function that you can use. So there are different steps that you can go through to make sure that you calculate the distance of each of these different data types. But of course, nothing is perfect in this world. So you always have different data sets with so many mixed data types. And so you have to find out how to deal with each of those. So imagine we want to calculate how similar these 2 people are. We have I, who for the feature of refund, he has no, and then we know that he's married. His income is 120K. Let's assume this is shillings. And then we have J. These are the features, right? So we'll look at how we can calculate the distance for these particular customers to see how similar these customers are. When it comes to numeric attributes, we calculate the distance differently. We use what we call the Minkowski distance, which I've included here. This is the calculation. So when Q is equal to 1, then that's what we call the Manhattan's distance. I don't know if we've heard of that one before, but then when Q is equal to 2, we call that the Euclidean distance. And really, Euclidean distance is really just the distance that would measure if we were to put a ruler between 2 different data points. What distance is that? These are the properties of the of distance measure. If we look at this particular diagram or this triangle, we have to make sure that there are certain properties that need to be met or looked at to make sure that we are calculating distance appropriately. So these are the different properties or requirements that should be satisfied. So the distance between I and J, which is this distance, which is what we're trying to calculate, should be a non-negative value, so it should be greater than 0, greater than or equal to 0. Then the distance between I and I, which is in itself, should be 0. The distance between I and J and I should be similar, so there should be a symmetric measure. And then lastly, the distance between I and J should be less than if we were to add the distance between I and K and then K and J. So we have to make sure that these properties are met when we are calculating distance. So if I take us back to the previous example that we had looked at, imagine we have 2 customers or 2 individuals, and these are the features. So we have a feature called refund. This customer did make a refund. He is married and he has an income of 120,000. Then we have J. J didn't make a refund. He's divorced and he has an income of 90,000. So how do we know how similar these customers are? Now remember, we have different features with different data types, right? So we have refund and marital status. These are categorical features or nominal.